So last time we were talking about this method, and I think that I didn't mention that people sometimes call this the symbolic method. It was basically this kind of dictionary between combinatorial operations on these various families of combinatorial objects and the algebraic operations in their generating functions. Okay. And so, if I had, I could have started the last time by covering up this labeled and covering up this exponential. Okay. So last time we talked about the symbolic method for combinatorial structures or combinatorial classes and ordinary generating functions. Okay. And so what I want to do today is do the labeled version of this. And so it's a very similar story, except that it's now geared towards structures where somehow the structures are on a label set. And you will see what I mean as we go on. But then the main point that I want to convey today is that when your set that you're working on is labeled, then it's usually better to use exponential generating functions. And then when you do that, what I said last time applies almost in the same way, but with exponential generating functions. So, okay, so today we consider combinatorial classes for combinatorial structures of size n on a labeled set of integers. Okay, so let's see what's the best way to say this. Well, maybe I'll just say for size n labeled by a set of n distinct integers, but usually those are just going to be 1 up to n. Okay? And so we're going to let a n be the number of such structures on the set from 1 up to n, and we're going to define the generating function to be sum over n greater than or equal to 0 of an, but now we're going to use exponential generating function. Okay? So this is what makes it exponential. Exponential generating function. So let's maybe talk about some examples. So we could have permutations, let's say, okay? And so if we have permutations, then the number of permutations on the set from 1 up to n is equal to n factorial. And then the formal power series, we get n factorial 0 to the n over n factorial, so we just get sum of 0 to the n, which is 1 over 1 minus. Or for example, we could consider cycles. Okay? And so here what I mean is a permutation that is a cycle. Okay, so you're thinking of putting your n elements now in a cycle with a prescribed order, let's say clockwise around the circle. Okay. So what is the number of cycles on n? Well, it's 1 over n times this, and the reason is that, a cycle is the same if you rotate it. It's going to be the same cycle, and so you can just start with the number 1, let's say. Okay, the number 1 is somewhere, and if you start there and you say, okay, who's next? Well, it's any of the other n minus 1 elements. Then who's next? Any of the other n minus 2 elements, n minus 3, and so on. So it's the product n minus 1, n minus 2, n minus 3 up to 1. So you get n minus 1 factorial. Okay. So then, what is the generating function for this? Well, if I put in minus 1 factorial here, then I'm going to get, and I guess I should say that this is only for n greater than or equal to 1. And so if I put in minus 1 factorial here, then I'm going to get the sum of z to the n over n for n greater than or equal to 1. And so since you're taking the GRE on Saturday, you know what that is, or you should remind yourself what that is. So the sum of z to the n over n is this, minus log of 1 minus. One way of seeing it is that is the integral of this one. So this is what I mean, and you could think of things like number of graphs where the vertices are labeled from 1 up to n, or number of posets where the elements are labeled from 1 up to n. This is the kind of thing that we mean. It's going to be useful to write down two kind of trivial things that are useful. So sets. Okay, so how many sets are there on? And I don't mean subsets. I mean just like the structure of a set. Okay, so how many ways are there to put the structure of a set on the numbers from 1 up to n? What I mean by that is just that there's one set with the elements from 1 up to n. So it's kind of a trivial thing. So for every n, the combinatorial structure is just the set of n elements. There's only one structure. So then, what is the generating function? Well, now if the ANs are equal to 1, then this is just e to the z. Okay. So that's a kind of a trivial one that plays an important role. And another one that's even more trivial and we discussed the analog in ordinary generating functions. It's just going to be basically the atomic class, meaning the atom here is the thing of one element. Okay, so the atomic class is basically going to be an atom of one element, and it only exists when n is equal to 1. Okay, so one if n is equal to 1, and 0 if n is not 1. Okay. So let me say again what I mean by that. So here I'm considering a family of combinatorial structures. So here will be all permutations of numbers from 1 up to n for some n. Here will be all cycles. Here it will be, for example, it will be the sets empty, the set 1, the set 1, 2, the set 1, 2, 3. That's this one. And here, there's only one thing, which is just one combinatorial structure that's just an atom, and it has one element, and that's it. Very boring. And so, of course, here I'm going to get that this is equal to z, because I only have a term for n equal to 1. Okay, so these are some examples, and now we want to play a similar game as last time and talk about what are some operations that we can do on these label structures. Okay. So the first one is just the same as last time. So a plus b is just going to be this joint union of a and b. Okay. So if you take permutations plus graphs, then the elements of that are things that are either a permutation or a graph. Okay. Now, so that's boring. Now let's define a product. And again, as we're doing this, you should be thinking that these combinatorial operations mimic the algebraic operations at the level of the generating functions, at the exponential generating functions. Okay. And so here, I want to invent a product that behaves like product over there. Okay. And in particular, given that these are not ordinary functions, probably the old product is not going to work. We need something new that takes the labeling into account. Okay? And so I'm going to write this like a little star here. Okay. A star B. And so what are the structures in there? So if I want the structure on the set from 1 up to n, then I'm going to partition n into two parts, A and B. I shouldn't use A and B, I should use S and T. To disjoint parts. So partitioning, for a number of ways, to partition and into two parts, and then put an A structure here and a B structure here. Choose an A structure on S and choose a B structure on D. Okay. So for example, if I consider permutations times graphs, then what you're going to do is that you're going to make a permutation times graph on a set of 8 elements. You split your set of 8 elements into, let's say, 3 elements here, 5 elements here, and then you permute these 3, and then you draw a graph on these 5. Okay. And that's going to be the structures in the product. Okay. So we can define sequences just like we did last time. So empty class plus the D class plus B star B plus B star B star B. Another way of saying this is that this is the disjoint union from k equals 0 to infinity of what I might call sequences of length k in B, where this is just the product B star B star B k times. And so what is this? Let me spell it out a little bit. So ways to partition or let me say choose an ordered partition and into a bunch of, like if I have B star B star B k times, then I need to do this k times, right? So S1 I'm doing something kind of goofy here, which is mixing two notations. So this notation is disjoint union, and this notation is also disjoint union, but this one is not. So disjoint union, okay? So I split my n as a disjoint union of k things and in order, okay? So this is an order partition, and these things are not empty. And then choose a B structure on each part. Okay. Okay, so that's fine, and it's a little too close to what we had last time. So this is a linear sequence, right? You really do the first part, and the second part, and the third part, and so these are things that want to live on a line, let's say. Okay, but sometimes things are not linearly ordered in some way, and we want to kind of break the order, and so we can do that by defining set of B, and this is going to be, again, I'm gonna do a bunch of examples, and I think this will be clearer once I do examples, but I just kind of want to write this and be done with it. So set is going to be the operation that's like sequence, except that there's no order. Okay. So what I do is that I consider the ways to choose an unordered partition of n and put a V structure on each part. Each is okay. Maybe let me kind of highlight here the part that's the distinction between these two. That again, this is here, this is ordered, and here this is unordered. Okay, and this is reflected in the name, right? When we think of sequence, we think of something that's linearly ordered. When we think of a set, sets are not. Sets don't come with a specified order. So let's do some examples, and I think this will all be clearer. For example, how can I express permutations in terms of this language over here? The class of permutations. Any ideas?
I want to say that is a set one.
So if I want to express a permutation as a set of things, then what are those things? So think about it. A permutation should be that you take your set of elements, you kind of separate them into groups, and then you do something to each group. So what should you do to each group?
Cycles.
You can put a cycle. So this equality is exactly saying that permutations can be written in cycle notation. Right? A way of thinking of a permutation is you split it into pieces, and in each piece you put a cycle. The result is a permutation. And why did we choose set here? Because the cycles of a permutation don't come in a specified order. That's why it's important to use set and not sequence here. But you might say, well, but actually, permutations, we often think of them as sequences. So why don't we use sequence? Can I also write this in terms of a sequence? So what is a permutation? A sequence of? The first way we think of permutations is just as a sequence of the numbers from 1 up to n, but in some order. So what is it a sequence of? Well, it's a sequence of singletons, actually, right? It's a sequence of one-letter words, each one of which is very boring, but together they form a permutation, right? Like 4, 3, 1, 2 is a sequence that starts with 4, then 3, then 1, then 2. And I can think of it as a sequence of what? Of boring things. A sequence of atoms. Okay, so I claim that this is, let's see what notation did I use here. Sequence of atoms. So let's think again about why this makes sense. So I'm saying to make a permutation, I take my ground set from 1 up to n, okay, and I split it into groups. And on each group I put the structure of an atom. Well, atoms only exist for groups of size 1, right? So when I split my n into groups, if there's any groups that are bigger than 1, then I can't put any atom structures on there, and this thing is empty. So the only way that I can get atoms is if I split it into pieces of size exactly 1. And if I did that, then what's a permutation? You take the numbers from 1 up to n, you make an ordered partition into sets of size 1, 4, 1, 2, 3, and then you put an atom, which is like doing nothing. And so that's why I have this. Some of the things that are more trivial are more confusing. I mean, this is more insightful than this, but I think this is a little bit harder to grasp than this. But keep thinking about it. I mean, this is true, and it makes sense after you think about it for a little while. Okay. So that's permutations. What about set partitions?
Ordered or
So if I don't say ordered, then that means that it's unordered. Set partitions. What is that? Well, this is my set partition right here. And so it's almost like it's the operator. So a set partition is doing this, and then what should I do to each block? It's just set. In other words, it's not doing anything, right? Just acknowledge the fact that there is a set of each size. So is this true? I'm realizing this is a little bad notation, because this is this operator, and this is this class. Okay, so let me say this is the operator, and this is this combinatorial class. Now, is this true? Set partition is a set of set. It's almost true, but there's one problem, which is that set partitions are not supposed to have parts of size 0. So I shouldn't put things of size here 0. But I'm wondering whether this matters at all. Maybe it doesn't matter, because actually when you do this partition, the partition is designed so that there's no empty parts. So this is true, actually.
How do you know that? That it's designed so that there are no empty parts?
Just because when we define set partitions, we define them so that the parts are not allowed to be empty. In fact, when we allow empty parts, then we call those weak partitions. Do you have a question or comment or something?
Well, just about the confusion about the class versus the operator, because you said you do this unordered partition and you throw some set in there, but the set could be the empty set. Right? It just knows that it got a set, but that set could have been the empty set.
But the thing is that when you perform to do something in set of set, what do you do? So set of a set. Set of the elements from 1 up to n. So what does that mean? You take the elements from 1 up to n and you make an ordered partition. S1, S2, etc. to Sk. And for each one of those things, okay, but those guys are not empty by definition. And then for each one of those things you put a structure on it, which is it's just like the acknowledgement that the structure exists. And it's like you never plug in n equals 0 here, because you never. It's like when you do this, you acknowledge that there are sets of size 1, 2, etc., but you don't care about whether it's a set of size 0 or not. It's kind of an unimportant distinction. What about graphs? To go somewhere different. Well, Given any graph, and here what I mean is a graph, so graphs where the labels are on the vertices. Okay? So every graph splits up uniquely into what are called disconnected components. Right? And so how do I express the fact that graphs have connected components in this language? Say that graphs, yeah?
Is it just a sum?
So I'm saying that for any graph, it can be expressed uniquely as pieces. So I mean, the thing about plus is that it's like right hand, left hand, right? It's like things that don't mix with each other. But if you think about it, let me try to restate the fact that graphs have connected components. What that means is that to build a graph, what I can do is look at my set from 1 up to n, then choose what the connected components are going to be, and there's some sets. And then on each set, make a graph, but make sure that that graph is connected. In other words, I have this. Every graph is made by choosing connected components and then making sure that each one of them is actually connected. Okay, so these are some examples of how this goes. Question?
Back to the set.
Mm-hmm.
Can you really have? Can k really go to zero from 0 to infinity? It seems like it should be from like 1 to n or something. If you can't have 0 sets. I mean, you can't partition into groups.
So
0.
yeah, so it's a good point. So the question is, why does this go from 0 to infinity? And I do want it like this, but let me explain why. What would k equals 0 mean? I agree that if k equals 0, you cannot really perform something like this. But this is meant to play the role of the trivial thing. Just like here I have a trivial thing, which is the trivial thing on 0 elements. And so if k is equal to 0 here, that only contributes this trivial structure on the empty set. This is the only time when k equals 0 appears. Whenever b has a size, then I need k to be bigger than 1. And I need to go to infinity because b could be arbitrarily large. So for each particular b of size n, I have to go from 0 to n.
Yeah.
But b can grow indefinitely, which is why I need to allow this to go to infinity.
Just like here, right? The connected graphs can just
Say that again?
the connected graphs can just keep growing
Yeah.
in terms of vertices.
Yeah, exactly. Connected graphs, they exist for every size. Okay, so again, the point of this is that these operations correspond to equations for the generating functions. And they go like this. The generating function of a plus b is just the generating function of a plus the generating function of b. Yeah.
Exponential.
Exponential. Everything is exponential today. All the generating functions are exponential. So this is just have to think about what it means, and you'll realize that I'm not saying anything.
Is there like any sort of standard notation for differentiating between ordinary generating functions and exponential generating functions? I mean, in terms of like, you know, if you write A or B here.
No, so actually, no, there is no standard notation that says, well, you know, here I'm using, I mean ordinary, here I mean exponential. So when you're writing papers, you have to kind of say, you consider the ordinary generating function or consider the exponential generating function. Or there's other kinds actually, so you have to specify which kind it is. And today it's all going to be exponential. Okay? Yes?
For those the last example graphs, if the graphs are already connected, then is it just a set where that it only contains the graph itself, and now you're now allowing basically for all the graphs that are unconnected, then we're going to split it up to all its connected parts, and that forms a set?
Right, so Tahir's question is how do I think of connected graphs on the left-hand side? Because some graphs are connected. And if they are connected, then this is going to be just the trivial partition of my ground set into only one part, and then I put a connected graph on there. And more generally, whenever I have a graph with k components, then only set sub k is going to arise here. Okay. So back to the generating functions, you can probably guess what this is equal to. We kind of designed this so that this is equal to a of z, b of z. And I'm going to sketch a proof of that in a second. What about sequences of size k? Sequences of size k.
Of something, right?
Of something, yeah. Thank you. Sequences of size k of b. What's the generating function of that? Well, when I write sequences of size k, I just mean b star b star b k times. And so it must be just this. Using this, I get that this is just b of z to the k. Right? And therefore, if I look at sequences of any size, then I get 1 plus b of z squared, etc. So it's just 1 over 1 minus b of z. And then what about set? Sets of size k. How much is this? For a particular value of k, what I'm doing is considering unordered partitions as opposed to ordered partitions, and then I do the same thing here and here. Which means that what I do here once, I do it here k factorial times, 1 for each order. And so there's just a factor of k factorial between these elements. It's the same thing as before, except that I should mod out by the order, and there's k factorial possible orders of my k parts. Okay, so I just get that. And so if I now write set b of z without restricting the number of things, then what do I get? I get 1 plus b of z to the 1 over 1 factorial plus b of z squared over 2 factorial plus b of z cubed over 3 factorial. So just e to the z of z. So yeah, so I'm good. So it's something incredibly simple. And so you can think of this as like the combinatorial meaning of taking an exponential of an exponential generating function. So, well, I kind of argued all of these as I was writing them, except that I didn't argue why this one is true. So let's prove this one. So let's see what's a good place to go. I think now I don't need this anymore. Maybe. It might still be useful. I might be able to squeeze it up here. It's a short proof. So proof of this one, okay? Of this part B. So what I want to say is that the number of structures on the set from 1 up to n in the product is what? That's why I didn't want to erase the product. So I'm supposed to partition n into two parts. And I don't know what size they are, so let's say that this has size k, this has size n minus k, but I need to sum over all possible values of k. And then what am I supposed to do? Oh, well, if I choose that this has size k and this has size n minus k, then how many partitions are there? Well, out of the n elements, I should choose the k that are here. So there's this many choices for the set S, and then the set T is just the complement of that. Now, how many A structures are there on S? Well, S has size k, so I get A sub k structures. And then how many B structures on T? I get this. Okay? So this is, let's say, the number Cn. Right? This is the number of structures in the product. Okay? Now, the thing is that my exponential generating function doesn't have as coefficients Cn, it has Cn over n factorial. So let me divide by n factorial. And then what's this? Well, n choose k is, it has an n factorial in the numerator, which cancels this one. And in the denominator, it has k factorial and then minus k factorial. And this is the coefficient of x to the k in a of x, and this is the coefficient of x to the n minus k in b of x. So what I'm doing here is precisely the product of a and b as exponential generating. So that's all there is to the proof. Okay. So it's pretty straightforward. But the value is in applying this. So we're going to apply this to a lot of settings, and we're going to discover a lot of nice things. So let's now put this to practice in a bunch of examples. Here, we're going to have to think about this a little bit more, but here I do want set greater than or equal to 1, I'm realizing. Okay. And I think if I try to think this through in front of you guys, I'm just going to get confused. So let's take it to the form why it is that this should be greater than or equal to 1 and not just set. But I'm realizing because of the generating function that it has to be there. So we'll make sure to clear that up in the forum. Let's apply this theorem to these three examples. So, generating function for permutations. It's this one. There we computed it. Is equal to set of cycle. Okay. Now, when I do the generating function of set of something, should be e to the something. E to the generating function for cycles. What's the generating function for cycles? It's this one. Minus log of 1 minus e. So, you see, actually, we derive this differently as taking the integral of this. And now it arises differently as the e to the log. So here we use that log as the integral of 1 over z. Here we use that log as the inverse function of exponentiation. So that's true. now I also get another expression. Since I have a sequence of something, then I would get 1 over 1 minus the generating function for atoms. Well, that's boring, because the generating function for atoms is just z. Okay? So it's boring, but it's true, which is good. Okay, so that's example A. It's kind of cute, but it didn't tell us anything we didn't know. Example B, set partitions. What is the generating function for set partitions? So do you remember, or in other words, what is the number of set partitions of a set of size n? Do you remember what that is called? So we gave this a number, and I just said the name, and I just said the name, and I didn't say anything about it. But these were the Bell numbers, and if I fixed the number of parts, then they were Stirling numbers. Maybe we can also write, if I am forced to have exactly k parts, then this is the generating function. But if I can have any number of parts, then this is the generating function. These were called Bell numbers. These are the Stirling numbers of the second kind. Okay, so what's this? Okay, I think I now understand what this is about. So sometimes the formulas tell you what's wrong. So if I try to apply the formulas to this, then what happens? Set partitions are set of something. So the generating function should be e to the something. It should be e to the whatever I have here. Now what is the generating function for sets? Well, if it was just sets, it would be e to the z. But I want to throw out, okay, so if it was just sets, it would be this. If it was true that set partitions was equal to set of set. But you see, the thing is that this is not even defined. Because if you remember, exponentiation is only defined when this thing has no things of size 0. In other words, let me say it in two different ways. Let me say it in algebra, and let me say it in combinatorics. So in algebra, in the ring of formal power series, whenever you want to do e to the something, we talked about how that something cannot have an independent coefficient. You cannot do e to the 1 plus anything, because when you try to write it out, it's not going to be converted. We talked about that. We talked about how if you want to do e to the something, then that something has to have leading coefficient 0. And e to the z does not have leading coefficient 0. And it had leading coefficient of 1, and I need to get rid of it. So that's kind of, an algebraic suspicion of why this should be like this. But combinatorially, what's happening? If you go back to your notes from the last time, when I defined these operations of sequence and set, last time we only talked about sequence, we didn't talk about set. But when I defined sequence, I told you that you only could take sequences of things that did not have things of weight 0. Because if you allow things of weight 0, then this was not going to be a combinatorial class. I think it was Kyla who pointed this out. So you can only take sequences of things that don't have things of weight 0. And so that's why I can't allow to have it's like you have to deny the fact that there could be an empty set. Like you can only plug in sets that have positive size. So I do this so that this is well defined, I get set partitions, and then I get this equation. And so for free, I get the generating function for Bell numbers, which we hadn't seen, and actually, this is not so easy to show without this machine. But with this machinery, it comes for free. What about the generating function for these guys? What is set partitions of size k? Of k parts. Right, that corresponds to that generating function for Stirling numbers where k is fixed. Well, if I want to force myself to have k parts, then I should just put a k here. Right? I should just have k parts. And then I get, I get to apply this formula. What is the generating function for set sub k of something? It's something to the k over k factorial. And that something here is called e to the z minus 1. So I get e to the z minus 1 to the k over k factorial. And I'll remind you that when we talked about Stirling numbers of the second kind, I wrote this down. And I told you that I could give you an unenlightening proof by induction if I wanted to, but I didn't want to. The reason that I didn't want to is that I wanted to show you this proof, which in a sense is the real proof that explains why the generating function is this. I would argue that this is much better than doing it by induction, where the proof might be easier to explain to somebody that doesn't know this machinery, but it wouldn't really explain what that identity is really saying. Okay. So that gives me this. And here we're starting to get some mileage out of this because these are two generating functions that we had not proved before. And in fact, I mean, we didn't even have to guess what they were because this machinery just kind of spits out what the answer is. You don't even have to try to guess it. So that's pretty cool. Now let's try to apply it to graphs. Okay, so we haven't tried to count graphs in this class. So we have the enumeration of graphs and the enumeration of connected graphs. Okay. Now what we've done, and the way that this is often used, is that this is what's easy, and this is what you get from it. In a sense, we're building complicated things out of easier things. So generally, the way this goes is that you know how to compute the easier generating function, and you get the more intricate generating function. But in this case, it turns out to be the opposite, actually. Because we want to count the number of graphs on n vertices and the number of connected graphs on n vertices. And it turns out that this is actually quite easy. Because if you want to have a graph on n vertices, and the key thing is that the vertices are numbered from 1 up to n, right? And so how do you choose a graph? Well, for each edge, you either draw it or don't draw it, right? And so basically for each pair of vertices, and choose 2 of them, you choose yes or no. For each one of for each pair of vertices, either you draw that edge or you don't draw that edge. So it's quite easy. I should say that enumerating graphs that are not labeled is quite hard. Because then you have to kind of figure out, there are different labelings of the same graphs. But enumerating labeled graphs is easy, it's just this. But you see, this is much harder because how do you keep track of, if you draw edges into a graph, how do you keep track of whether it's connected or not? That's harder. But the thing is that now from the machinery we can just get a formula for these guys from these guys. Right? Because this generating function is the exponential of this one. So this one is the logarithm of this one. And so what I get is that this is the logarithm of this. Where now, this is quite easy to count. And so there you have it. This is a formula for the number of connected graphs on n elements. I mean, it's not the easiest formula in the planet to use, but actually you can feed this into any software that can compute things like this, and you can compute the first any number of terms. I mean, any reasonable number of terms by just plugging. And the fact is that this is the generating function. You can't look for an easier formula if it doesn't exist. This is as simple as this gets. Okay. All right. So that's how this is put into practice. And I want to do a little bit more of this kind of stuff. Because now what I would like to say is, okay, so I mean one thing you should realize is that this technique is useful in a lot of contexts. Whenever you have some combinatorial object that decomposes into connected pieces like this, and this happens to be set of this, then you can apply this technique and relate the generating function for all objects to the one of connected objects. But I want to push this a little bit further now, and I want to try to count, for example, what's the number of graphs that have exactly k components? And I can also get that from this stuff. So what if I want to count by connected components? So let me just repeat what I said, that if a combinatorial object B decomposes uniquely into what you might call the connected components or the irreducible components, so that B is equal to set of A, then we already saw that B of Z is equal to E to the A of Z. This is extremely general. But now what I want to do is ask myself a slightly harder question, which is, what if I want to compute the number of B structures on n elements having k components? Okay, so this is B objects on n having k components. So, okay, this depends on two parameters, and so the standard trick is to introduce a generating function of two variables. So for n, I use the same z that I was using, and for k, I'm going to use the letter y. And you might wonder, why is it that you're putting y to the k instead of y to the k over k factorial? And the answer is that this is what gives you the nice result, and so this is how we do it. So it turns out that for this kind of thing, you still want to think of this. I mean, you want this to be an exponential generating function in z, and you want it to be ordinary in y. And if you do it that way, this couldn't be simpler. It's e to the y a of z. And given that e to the a is b, this is just b of z to the y. So you see what I'm saying? I'm saying that, for example, for graphs, if I want to know how many graphs have n vertices and k connected components, okay, so I sum over all n and k. All I have to do is take, okay, so let me finish this, e to the n over n factorial. If I want to count things according to their connected components, you just first forget about the connected components, and you just count them. So this is what you would have if you're not paying attention to connected components. And you just do this magical thing. You just do this and raise it to the y. When you do that, you get your formula for GK of n. Pretty magical. And what does it mean? So let's think exactly about what this means. So forget about this for now. Okay, so this starts, I don't know, 1 plus z squared plus, I don't know, I can't really do this in my head. Let's imagine this is 1 plus z squared plus 2z cubed plus 3 z to the 4th over 4, etc. It's just something in z, okay? And then what am I doing? I'm just taking that thing and raising it to the y. And how do I do that? I use the binomial theorem. 1 plus something to the y is whatever the binomial theorem says that it is. So I get this big thing. And whatever that big thing is, it exactly counts things by their connected components. That's it.
I'm still confused on why we're writing it in the ordinary way for y to the k.
So it's more the opposite thing. It's more like if you somehow thought, well, let me take b of z and raise it to the y and see what happens, you just get that this is what happens. Okay? If I try to force this, then the fact is just that there's no nice formula for this. This magical trick doesn't work. It works like this, but it doesn't work for the exponent, for the ordinary generating function in y. And this is something that, I mean, in combinatorics, it takes some experience. When you're trying to enumerate something, we have to make these choices, you know, like which variables go in exponential and which ones go in ordinary. And really, we just make the choice that gives the nicest answer. Okay. And so here, I think it's clear that this is the right choice, in that, you know, the formula for this is extremely easy. But actually, I don't think that there is any nice formula if you were to put over k factorial here. Or like this formula, right? So why did I choose to Bell numbers should have an exponential generating function? Because look at how nice it is. Whereas if I wrote it like this, I don't know what it is, and it's not going to be as nice. Really, we just go with whatever gives us the cleanest answer and the best way to compute them. Because again, you have to keep in mind that if you actually want to compute these numbers, then you have to deal with the complexity of these functions, right? And so plugging this into Mathematica or Maple or whatever you use, Sage, it will take you no time. So that's why you would prefer this one as opposed to some other ugly thing. Here it's just kind of the nicest thing that's available, so that's why we prefer it.
So in this last class that you said you didn't use operation set. Can we also have done it in the last class? is there no such? Because here there's no.
So
label in-
Servando's question is, why did I not use set in the last class?
Because there's no labeling, so there's
And it's because set starts by taking your ground set from 1 up to n and partitioning it into pieces. We take a set partition. In the last class, our ground set didn't have labels, and so it wasn't really a set. It's more like, yeah. And so you can't really take a set partition of something that doesn't have labels. Right? But you could still think, what would be an analog of this in the ordinary case? Maybe there is something, but it cannot be set partitions. Okay, so I was going to prove this for you, but actually I'm thinking that writing down a proof of this might help you understand why this all works. And the proof is actually not so hard, but I mean, it just takes kind of going in there and seeing what just happened. So far, I think a lot of what I've done has been kind of magical. And this is also kind of magical, but I think you should kind of go in there and see what the meat of this is. And you'll see that it's not so much. So maybe I'm just going to leave this as an exercise to prove this. But really, it's not too hard. You just have to see what everything means and just carry out a computation. But I think maybe instead of getting that proof, I just want to apply these techniques and show you some of the results that we can prove. So let's do some more examples. Oh, actually, I want to do another example of this one. And so I shouldn't have erased what I just erased, but okay. So what happens when you apply this to permutations? So we said that permutations were sets of cycles, right? And so then from this we got that 1 over 1 minus z equals e to the minus log of 1 minus z. But what if we now pay attention to the number of components? What do we get? What is a permutation with k components here? Well, in this case, the components are the cycles. And so here I'm talking about permutations of n elements with k cycles, and we have a name for that. This was that number C of nk, which was the Stirling number of the first kind. Permutations of n into k cycles. Summing over all n and k. So this is now extremely easy to do because this is just the enumeration by connected components, and so all I should do is just enumerate as if I didn't care about the connected components. That's the enumeration of permutations, and just raise it to the y. That's it. Okay. So what's this? This is 1 minus z to the minus y. And let's actually multiply this out. Sum over n greater than or equal to 0 of minus y choose n minus z to the n. But now let me remind you that this is the same thing as we had this combinatorial reciprocity, right? That said this was what? Y multi choose n. So this is sum of array greater than or equal to 0, and I'll remind you what this is. This is y times y plus 1 times y plus 2 up to y plus n minus 1 over n factorial z to the n. Right? By the way, if you forgot about this, you can skip this step. Just write down what minus y to choose n is, and you're going to get this. So what did I just do? Well, if you just look at what the coefficient of z to the n over n factorial, then what I did is that I proved that the generating function of c of n k y to the k is equal to this. And this is something that we did very manually by doing an induction proof that was not very enlightening. Okay. But again, here I just wanted you to see that that identity just comes out for free, and you didn't even have to guess it to try to prove it by induction. It just comes out of the game for free. So I guess Stirling numbers are the first kind out of this. Okay. Cool. Let me do one more example. Involutions. Let In be the number of permutations pi of n such that pi inverse is equal to pi. These are the permutations that are their own inverse. I want to count them. Turns out to be extremely easy now, because pi inverse equal to pi. This is the same thing as saying that the identity is equal to pi squared. This is a group of permutations, and so I can perform these operations. Identity is equal to pi squared. Now, when is the square of a permutation equal to the identity? If you think about it in cycle notation, you'll see that what happens to a cycle of length 1? Pi of I is equal to I, so pi of I is equal to I also. In a cycle of size 2, let's say it's I and j, you have pi of I equals j, pi of j equals I. So pi of both of them are themselves. But if you have cycles of bigger length, I, j, and k, then pi of I is going to be j, pi of I is going to be k, which is not going to be I. Right? And so you just can't have any cycles that are bigger than 2. So this is true if and only if cycles of pi have length 1 or 2. So then, what do I get? I get that the generating function for this is basically taking my set n and partitioning it into things of size 1, into cycles of size 1 or 2. And there's only one cycle of length 1 for a given set of size 1. And if I have 2 elements, how many cycles of length 2 do I have on those 2 elements? So it's just 1. A goes to B, B goes to A. So I have just 1. That's it. So I get the formula for involutions with almost no work. Yeah.
Is there a relationship between that and Dono tilings, as we did before? is like each cycle is 1 or 2.
So this is reminding you of the formula 1 over 1 minus z minus z squared for domino tiles of a 2 by n. It's almost like the exponential version of that. But I don't know that I can say anything more concrete than that. There is a similarity, but I don't know that I can say much more about it. Let's talk about derangements. So let dm be the number of permutations pi such that pi of I is never equal to I. Sometimes they talk about this in like a problem in a party where n people go to a party, they get really drunk, they drop their hats, and then on the way out of the party, everybody just grabs a random hat and puts it on. And the question is, what's the probability that nobody got the right hat? Those are the derangements. Well, it turns out I can actually just write what the formula is. Because, again, if we look at this in cycle notation, having no fixed points is the same thing as having no cycles of length 1. And so here, what I have is just set of a bunch of cycles, except that I'm not allowed cycles of length 1. I am allowed the other cycles. So this is the generating function for cycles, except that I am not allowed the first z. In other words, this is minus log of 1 minus z. This was permutations, but now I just have to disallow the cycle of length 1, so I just subtract z from it. And so what do I get? I get e to the minus z over 1 minus z. And actually, it's quite easy to find the coefficients of this thing and get that this is n factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial, etc. up to 1 over n factorial with whatever the appropriate sign is. You see, this is this number approaches 1 over e. So this is approximately n factorial over e. So this is a very famous problem in probability, where the probability that everybody got the wrong hat is basically 1 over e, or it converges to 1 over e as the number of people goes to infinity. And again, there's several other proofs of this, but here it just comes for free from the general machinery. Okay.
So remember the last class, once you had the generating function, the ordinary one, you said there was like a way to visually get the recursion formula. Is there such a thing? Like for example, how do you
So the question is, last time we had some generating functions. So actually, let me repeat what I said last time. That if you have a generating function, and the answer is a rational function, then you can use the denominator of the rational function to give you a recurrence for your numbers. Actually, that's a fact of a power series. And so if for some reason it happened that the exponential generating function was rational, then you could do the same thing. But I think the problem is that this almost never happens. Exponential generating functions don't tend to be rational. These ones aren't, right? And they more tend to have things like e's, and you can see why, right? Because it's kind of buried in the theory that you have e's. Can you get recurrences out of this? You sometimes can, and it ends up involving more derivatives, I would say. And it's a less established thing. I mean, in the case of rational generating functions, it's very clear what to do. And here you have to be more creative. But often you can pull it off because, like, the derivative of e to the z is e to the z. And so often you can. Well, maybe instead of saying more about this, I'll just show you some examples next time. But yes, I mean, sometimes from the generating function you can kind of backtrack and try to get a recursion for your sequence, but it's not as clear and easy as it is in the case that we used last time.
Okay, so another question. So how did you see that exponential generating function and know that d of n equals m?
Oh, no, from here to here, so I prepared class notes, so I actually, in my notes, so you should look at my notes, this is carried out, but I'm skipping some steps. Yeah, but not too many. I mean, you know what these power series are, and you just kind of multiply this out and you get this. But yeah, so moral of the story, very important for you to remember, is that if you're trying to enumerate things, if they kind of want to live on a line, that's usually when you want to use the ordinary generating functions. Whereas if they're kind of like not linear structures and it's more like they come with a labeling by a set, then generally it's exponential generating functions that you want to use. So if they have labels, exponential. If they don't have labels, ordinary. It's roughly true. It's more of an art than a science, and so it's not as algorithmic as, I don't know, taking derivatives, but it's a good kind of thing to keep in mind. Okay. All right, let's stop here.
So for trees, if you were dealing with trees, you probably want to use exponential.